In a world of busy supermarkets and increasing labor costs, restocking shelves takes time, people, and money, and sometimes things don't go quite as planned. That's why we set out to build a robot that could see, think, and act on its own, one that could find items, pick them up, and deliver them to the right shelf completely hands-free. Introducing the Atlas, a low-cost, small-scale autonomous supermarket assistant. Fitting inside a 20cm cube, this robot can drive up steep ramps, reach multiple shelf levels, and navigate through tight supermarket aisles, all for under $200. Armed with sensors, code, and more late nights than we'd like to admit, the Atlas brings autonomy to life, a compact robot with the brainpower to take on the supermarket floor. So how does the Atlas actually work? Our design brings together four main subsystems: mobility, item collection, vision, and navigation. Each one was designed from scratch to work together as a single intelligent unit.
The mobility system is the foundation of our robot. Designed to be both powerful and precise, it needed to handle steep supermarket ramps, turn tightly between narrow aisles, and stay stable no matter what we throw at it. At its core is a rear-wheel drive differential drive system, powered by high-speed 50:1 gear ratio motors, providing the torque needed for fast acceleration and confident hill climbing. The front wheels sit on a custom axle and low-friction mount, allowing smooth, effortless turns on any surface. Together, these features give the robot the agility to zip between shelves and the strength to tackle steep inclines, all within a compact, low-cost design. Of course, none of this would run without a solid power system. Our robot is powered by an 8-volt battery that acts as the heart of the whole design. The power first passes through a main switch, our robot's on-off button, before heading to the Pi motor driver hat. From there, power is distributed to the Raspberry Pi, the camera, the nano microcontroller, the ultrasonic sensor, and the motors themselves. To supply the rest of the electronics, a small buck converter steps the voltage down to 5 volts. This lower voltage powers the LED array and the item collection system, keeping everything running smoothly and safely. It's a simple, efficient setup that keeps every part of our robot working together seamlessly.
In order to fill the shelves, the robot needs to be able to collect and place the products. The collection system of the robot handles this, using multiple servo motors to grab and lift the products to precise positions. The motors receive commands from the navigation system, telling them what object to pick up and at what level shelf to fill them. 2 servo motors are connected to a parallel linkage system to raise the products to the different shelf heights. Another servo motor is connected to a rack and pinion system to apply compression to the products to grab them. The collection system has predefined measurements to close in order to collect different objects, such as a bottle, a cube, and a rectangular box.
To navigate the supermarket and deliver items autonomously, the robot first needs to see. This is where the vision subsystem comes in. Using a combination of a camera and an ultrasonic sensor, it can detect objects and estimate distance and bearing in real time. The camera streams to a Raspberry Pi 5 for processing. Color segmentation, contour, and geometric analysis using the OpenCV library in Python allow the robot to distinguish different object types, separating cubes from bottles and markers from shelves. For range estimation, the system combines pinhole camera geometry with ultrasonic sensor readings. The camera provides relative distance based on object size and position within the image frame, while the ultrasonic sensor supplies absolute range confirmation with its echoing pulses. This dual sensor approach gives accurate perception for both small and large objects, even when partially blocked or during lighting changes. All this processed data is then passed to the navigation system.
The navigation system integrates all subsystems into a complete product. It reads an order file, which has items, pick stations, and target shelves, and executes a behavior tree governed by a state machine with destination-based variants. Sensor fusion, which has the camera, ultrasonic, and motor encoders, run a closed-loop controller to minimize over and undershoot. Because encoder response vary with voltage, we built an average lookup table from batch tests to stabilize linear and angular accuracy. Using predefined linear and angular limits, the robot advances states only after confirming it's within the required zone, and always aligns to a bearing limit before moving. While approaching targets, the ultrasonic sensor continuously refines range so the robot nudges forward or back to the exact standoff distance. Servo heights on the grabber are programmatically set to suit tasks, maximum when using the camera or ultrasonic, a tested ramp height for climbing, and predefined positions at shelves or objects. This coordination ensures consistent localization, motion, and handoff at every step.